Okay, just give me a second here. Okay, test. Okay, all right. Okay, so we have discussed example 1. So the solution is just that we will add E1. So we will add the electric field contributed by the line charge at this point, and also the point charge, at this point here. So, and also the point, this is the point charge. And so the point of interest is 403. So I have calculated the electric field. And now, so we can add both. Okay, so 0.18 minus 0.1389. Okay, so we will get about, okay, I can round this up as negative 0.14, just, I mean, for the sake of easy calculation. So I will just write it as negative 0.14. Okay, so we get now is 0.24 x cap epsilon naught plus 0.04 over epsilon naught z cap. So the whole thing divided times 10 to the power negative 3. So the answer is 240. So the answer D So it's 240 micron x cap plus 40 micron z cap. Okay, so that's the answer. Okay, so since we have, I have provide some preliminary explanation regarding flux. So electric flux, uh, simple definition, or a simple demonstration, or simple illustration. You just have to you just have to imagine that a vector field. So electric flux. So electric flux. So a vector field, okay, through a surface. Let's say this surface here is an is an arbitrary surface, arbitrary open surface through the surface. Okay. So a vector field. So when I talk about field, it means that there has values in space. So each of the point in space, or represented by vector, they have a value. They have a value. So that means it's not necessarily constant not necessarily constant along the vector line. So they have values in space. So when I talk about in space, that means a three-dimensional space, in real space, like what you are sitting in a room. So everywhere around you are space, right? So the electric field that passes through, whether it's a closed surface or even surface, so that is electric flux. Sorry, that's that's flux, electric field flux, right? So Gauss law formulated says that if we apply a closed surface, uh, in space, so this closed surface here can be any arbitrary closed surface. So for example, like you have a plastic bag. So for example, you have a plastic bag. So the plastic bag can be arbitrary shape. Okay. So a closed surface. So imagine you have a plastic bag, you store something inside, and then you wrap it around at two ends, right? Then that plastic bag that store your barang-barang, I mean your the goods that you want to store. So it depends also the shape of the goods, or the shape of the things that you want to store inside the plastic bag. So the shape of the plastic bags will depends on what is inside the plastic bags. So in general, a closed surface. So what I'm trying to point to you is the closed surface can be any shape. Okay. So Gauss law states that the flux coming out from this closed surface, is equals to the charge enclosed, as stated here. So just by a simple statement. So this is Gauss law statement. The electric flux through any closed surface is equals to the charge enclosed, and therefore it is the electric flux, dot I mean, the electric flux multiply the surface area, which is equals to the charge enclosed. So which is equals to the charge enclosed. Okay. So if let's say Q, the total charge enclosed, I mean the surface, the closed surface that enclose the charge. Okay. And this charge here can be represented by a volume charge density. So therefore, the total charge is equivalent to the volume charge density multiply the volume, right? So it means that if we have an imagine, I mean this Gaussian surface, this closed surface here, enclosed in space. Imagining, I mean basically this is a mathematical uh, definition for Gauss law. So we have to imagine that there's a closed surface enclosing. I mean, you have to imagine that like a balloon in space, and the flux coming out, and the flux, electric flux. So imagine that there is a vector field, the vector field coming out from the balloon. So this vector field here, if we multiply with the surface that is perpendicular to, I mean, if I mean we perform a dot product with the surface area of the balloon, and we sum everything, and we add everything, which is represented by the integration. So that means we sum everything. That is equals to the charge enclosed. And this charge enclosed, we can also represent it as a volume charge. So assuming that you have a balloon, you have a sphere, right? You have a spherical sphere with all the point charge that form a volume, or as a sphere. Okay. And this point charge here, accumulated point charge in the sphere, the total of it is capital Q, as capital Q. So I will repeat my sentence. So let's say you have a small point charge Q, small q, a small point charge, small q here, and then it is accumulated many in space, and it form a sphere, a closed, that is, you accumulate all the point charge in space and form it as a solid sphere. Yeah. So the total charge in the volume, is Q, right? So it's capital Q. So rho V, as we know, it is called the volume charge density. So volume charge density. So if volume charge density, it is represented by charge divided by meter cube. And this evaluation, the integral evaluation is correct, because volume charge density multiply with volume integrated over a volume is equals to Q, is equals to the charge. So now, I mean, why is it represented by an integral? You ask. Let's say, why is it represented by integral? Why cannot we just multiply rho V times the volume, and then we got Q? The thing is, we cannot do that directly, because we haven't really defined what is the surface. So I can have a surface like this, a cube. I can have a surface like this. I mean, I can have a volume like this. Okay. sorry, I can have a volume like a cube. I can have an arbitrary volume like this. So let's say inside there's a charge, yeah? There's some kind of a charge density. I can have a volume like this, okay? So we haven't really know what is the charge distribution. So because we haven't know the charge distribution, and therefore we have to come up with a general statement, a general representation for Q, which is the total charge. So we haven't know what is the charge distribution. So the application, the subsequent application or subsequent example that you will be exposed to, all the charge distribution is going to be symmetrical. It's going to be symmetrical. So, and you will ask, what is it? What about if not symmetrical? Okay. If it's not symmetrical, then we are going to apply another uh, another mathematical tool. And of course, this mathematical tool will be based on our knowledge about Maxwell. So in this chapter, I will try to lead you to the formulation of Maxwell equation. So 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 if the charge distribution is not symmetrical and non-uniform, then we have to opt for a more general kind of solution, which is called the Laplace or Poisson equation. Okay, but in our course, we will only look into one-dimensional Laplace equation or Poisson equation, only one-dimensional. So in general, you have 3 dimensions. So we have x, y, z. However, as I said, in our course, we will only look at one dimension only. So either x or either y or either z. So it depends on the charge distribution. Okay. So the symmetrical charge distribution, it is only depend on x, y, or z. So we have cylindrical symmetry. We have also spherical symmetry. So we look at each one of them in the subsequent example. Okay, so divergence theorem relates what is the surface integral with volume integral. Sorry. Okay, so before we move to establishing what is the first Maxwell equation. Okay, it should be named Gauss Maxwell equation, but in general they just call it Maxwell equation. Okay, divergence theorem. So if you heard of divergence, the definition of divergence. So in vector calculus, the definition of divergence, not divergence theorem, divergence. Okay, it is defined as the del operator delta dot with definition of divergence of vector, let's say vector A, yeah. So dot with A, the vector operator, the delta dot with A, which is equals to 1 over del V integrate with A ds. Okay. Sorry, maybe I need to rewrite this again. I need. Okay. So what does this mean is, so if the as the name implies, divergent, as the name implies, divergence of a vector, it means that you want to measure how diverge, what is the spread, what is the spread of the vector field. So to give you I know you have somehow learned this before, divergence vector, I mean del dot A, the divergence of a vector. So to give you a physical idea is that, so your tap, right? If you open your tap, water tap, I'm saying your water tap. So some of your water tap have a very narrow stream of water, right? So from I will just draw it briefly here, then I will erase it. So you have a water tap. So I'm just giving you an analogy, yeah. So you have a water tap. So if you turn on the tap, you normally we have a stream like this, okay, a stream like this, and some they have a stream, some kind of stream which is not narrow. It can be a bit of spread, which is like this, like this, okay, okay. So it depends on the pressure, of course. It depends on the pressure as well, and as well as the opening of the tap, right? So normally we have a narrow stream that is typical. So here we'll give you an idea. If let's say let's say a narrow stream, so the divergence is not that high compared to the spread, right? So if we assume that you have a closed surface like this, let's say you in I'm not sure about now. I don't think you have seen this before. Those days when we do not have any water filter, yeah, because of we do not have water filter at the time, and especially in the village, or we call the kampong. So we do not have this type of luxury. And what we do is, in order to filter out um, those what they call it, the corroded piece of metal, yeah, because we have a pipe that too old, okay, and the underground pipe that used to deliver the water to us. So that pipe, and I mean, it's not only one household. I mean, typically all the household will experience this type of condition, which is the corroded water. I mean, the in Malay we call karat, yeah. So it's a bit yellow, and then there's some debris. There's some debris sometimes coming out from the water tap. So what we do here is how we try to filter as much as possible. we have some kind of cloth. So we have some kind of a cloth here. Okay. So assuming that this cloth here is a closed surface, like a closed surface, right? So if it's coming out from this cloth, if it's coming out from this cloth, so the divergence, so we have a divergence. I mean we can say that this is the divergence of a vector field. So we can this as an analogy of what is called divergence. And this is called positive divergence. Positive divergence. And what about if, let's say, you have a closed surface like this and nothing comes out, only goes in. Nothing comes out, only goes in. So here is the positive divergence. And as opposed to what I try to what as opposed to what I'm trying to explain to you here, this is going to be negative divergence, right? Because only not everything goes in, nothing comes out. So it's a negative divergence. And again, here you can use an analogy to your sink. So I give a analogy with water tap. So you can use an analogy for a sink. So I mean everyone should know what is a sink like, right? So the water flows and all the water flow through the sink, right? So the sink is like absorb all the water. Yeah, the flow through that sink hole. And this become our source, right? This become our source. And here we measure the divergence. Okay. So now, if let's say this volume here, this volume here, this volume here, I mean this cloth, which is the closed surface, and it shrink to zero. Not entire zero, I mean towards zero, tends to zero. If let's say the surface, when it wraps around the tap, so it contains some kind of volume, right? So what if the whole entire volume shrink to a dot, shrink to a zero? So that means that is your point source, right? That represent a point source. Okay, now so it's a bit difficult to it's a bit difficult to imagine. So I will give you an example and on um, how are we going to apply this. So what I'm going to explain here is going to relate the divergence theorem. So now, assuming a point charge, so assuming a point charge at the origin, let's say we have a point charge here at the origin. So this point charge represent by a dot. So a point charge Q, a point charge Q. Okay. So imagine that this point charge in three-dimensional space located at the origin O. Yeah. So imagine that a spherical and imaginary surface, a spherical imaginary surface. spherical imaginary surface. Okay. Enclosing a spherical imaginary surface enclosing the point charge. So therefore, we want to measure the divergence now. So we knew that the electric field coming out from a point charge is equals to Q divided by 4 pi epsilon naught r squared, right? At the direction of r cap. So imagine that now the spherical surface, this spherical surface, imaginary spherical surface, enclosing this point charge having a radius r as well, Okay. So by definition, therefore, by definition of uh, divergence, this implies the divergence of E, okay, the divergence of E is equals to the limit of delta V tends to 0 1 over delta V E dot ds. Okay, so we are integrating um, the flux. Basically, we are integrating, we are evaluating the flux coming out from the spherical surface. So this is the flux, right? The flux term. So we are evaluating the flux through the surface, through the spherical surface. And so what would be the surface of, differential surface of a sphere? So the differential surface of a sphere, that is this surface here, which I highlight. So here will be, this arc length is r sine theta d phi, and this arc length here, will be r d theta. Okay, so the vector, the direction of vector, which is normal to this surface, surface here, which is going to be r cap, right? So is r square sine d theta d phi r cap. Okay, so r cap and r cap, dot r cap. So the entire evaluation now, it becomes a constant. There's no longer vector here. So r squared, okay, r squared and r squared can be cancelled off. And leaving only sine theta, d theta, d phi. Okay. So now, so if we evaluate, this term here, 1 over the, I mean, the integral becomes q over 4 pi epsilon naught times this is evaluating phi is 2 pi, and evaluating sine theta is negative cos theta, and then the limit is from 0 to, so the negative cos theta evaluated from 0 to pi, it gives me 2. Yeah, it gives me 2. So 2 times 2 pi is 4 pi. And therefore, I have now, q divided by, so 4 pi, 2 pi times 2, here is 4 pi. So 2 pi here, and the other square bracket, the evaluation is 2. So 2 times 2 pi is 4 pi. 4 pi and 4 pi can be simplified, and only leaving me delta v epsilon naught. Yeah. Okay. So here delta, so you can see it q delta v, right? So if the limit of delta v, so this represent the volume. So the volume that enclosing the point charge. So if we shrink this volume now, if we are going to shrink this spherical surface, this spherical volume into towards this point charge, so it's going to be rho v divided by epsilon, right? So that is my divergence. So rho v represented by rho, where rho v is q over delta v. So basically it tells what this means is, when the sphere, when this imaginary spherical surface, I mean when you enclose something, so the space that you enclose, by this spherical surface, it contains some kind of volume. So when this volume shrink to zero, tends to zero, when it tends to zero here, it means that it is the charge distribution at the point, right? It is the charge distribution at this point. So this is called that is why it's called the point charge. Okay, so this is a charge distribution at a point. So this is what it means. So now, so as I'm trying to tell you here is, if from this definition, so from this definition here, so I'm going to further tell, I'm going to further extend this knowledge to be how are we going to relate the divergence theorem. So since we have del E, the divergence of the vector field E coming from a point charge Q, and which is represented by rho V over epsilon naught. So even though our discussion here is based on point charge, but in general we can extend this as the in general case. Yeah. And now you can see that I cross multiply this term. If I multiply with epsilon naught, so this is a constant, right? Relative permittivity of free space. Okay, so this is going to be delta epsilon naught E rho V, right? So anyone can tell me what is epsilon naught, the permittivity of free space multiply electric field? What is this? What is this term here? What does it represent? It's correct. The electric flux density is correct. So I can rewrite this. So I can rewrite this term here as delta D rho V. Okay. So now if I'm going to integrate both sides in terms of volume, because since this is a volume charge density, so I'm going to apply a volume integration. That means a triple integration of this. So if I apply integration volume on the left hand side, I must also apply integration volume at the right hand side. So if we compare this term now, with Q, this is our enclosed charge and enclosed charge, right? Right, this is an enclosed charge here. So this is Q. So what we are going to relate now is the surface charge integration S, because from Gauss law we already know that rho V, the integration of the charge density over the volume, and this volume here is actually enclosed by this surface. This volume here is enclosed by this surface. Yeah. So therefore we have now rewriting this term here. So this is equals to so we have relate the surface integration, I mean, sorry, the surface integration, or the double integration with the volume integration of the divergence. And here we establish the divergence theorem, which is now, if you compare back, is the same, right? So of course, if you see that if A replaced with E, then we have actually the same thing. Yeah. Okay. So this is divergence theorem. So divergence theorem, uh, and of course, um, we can in fact, without my detail, I mean, without this detailed explanation here, we can actually just accept solely, just accept, we can accept, because this is a theorem, so we just accept, okay, the closed surface integral is equals to the volume integration of vectors. Yeah. So this is a flux, this is a divergence. So this term here is flux, this term here is divergence. And therefore, if we compare, to the Gauss law, okay, starting from the divergence theorem, so I'm going to replace A with D. Yeah, I'm going to replace A with D. Yeah, I'm going to replace A with D. So say that, so I'm going to rewrite this again. Divergence theorem. So from the previous page, from the previous definition, uh, divergence theorem of divergence theorem. So if I replace A with D, it's going to be this form here. So, however, on my left hand side, based on Gauss law, it is V dV dV, rho V times dV. So it's a volume integration. And therefore, if we compare both side is also volume integration. That represent, and this volume, I mean, the volume that, I mean, the volume of interest is the same as, on the left, and on the right is the same. So which is defined by the closed surface, and therefore we can directly write this as equals to rho v. So if you compare this, oops, sorry. So if you compare this, you compare this term and this term here, that based on divergence, the definition of divergence, it is the same. It is the same, right? So this is the theorem. From the theorem, we establish the point form. I mean, the angle that I'm coming from is the definition of divergence. So don't mix up divergence the definition of divergence and divergence theorem. So divergence is the divergence of vector A. We say that is the limit of the volume. So based on the imaginary surface that I just mentioned, which is shrink to 0. So what I did here is I use a point charge as I use point charge as an example. So it's much, I mean, it is, I think it will be much easier to relate in this way. So as I said, so as the limit of the volume tends to 0, the volume that defined by this imaginary surface tends to 0, and therefore the divergence of vector E, it is equals to, it is equals to the charge density. The charge density at a point, yeah, because I'm using an example of point charge. So this is defined by the charge density at a point. But in general, it is equals to, it is equals to the volume charge density in general. So please remember, I'm saying that using this example for point charge, I'm just trying to tell you the development of this theorem, that using Gauss law and the application of divergence theorem, and how is it relate to the point form of Gauss law. So this is the point form of Gauss law. Sometimes they call it differential form, and we have the Maxwell equation. So here rho v is the divergence. So the volume charge density, it is equals to the divergence of the electric flux. So this is called the Maxwell equation of in point form. And this is the Maxwell equation in integral form. So normally we call this Maxwell equation in integral form. So we have two forms. Sorry, can I excuse for a while? I have a important call. Sorry, guys. Come back to our discussion. Sorry about that. So we have Maxwell equation in integral form. So we have basically two forms. So each of Maxwell equation, we have altogether four equations, and we are not going to what you learn in this course. The four equation doesn't take into account of time. I mean, doesn't take into account of the time variant, the time variant for the electric field or magnetic field. So if we take into account a time variant, then the Maxwell equation there will be some changes in the Maxwell equation. So for now, we will look into only the static point of view. So electrostatic and magnetostatic. So there's no time variant. So it is time invariant. So when I say time variant or time invariant, that means the vector, i- the amplitude, the magnitude, and the direction of this electric field vector changes in time. So for static field, electrostatic and magnetostatic field, the the vector never changes with time. Okay, I mean those field doesn't changes with time. Okay, now so for each of the Maxwell, as I said, we have four Maxwells. For each of the Maxwell equation, we have point form and integral form. So the Gauss law, the first one that has been uh, exposed to you, is the first integral form. So we have the Maxwell equation in integral form, and we have um, and I've explained using the divergence definition, and from a divergence definition by using an example, using a point charge example, and here leads to the differential form of Maxwell equation. So now we are going to look at some example. How are we going to apply Gauss law? Mainly using the integral form. So how, if you look at the two equation now, so one is the unknown from Gauss law. One is d is unknown, and we want to determine. Usually for the first form, the integration form, usually d is unknown, and we want to find out d. However, uh, for the point form, usually d is known, and we want to find out what is the charge density. That is the typical application of Maxwell. I mean, for this Maxwell equation or Gauss law. So how are we going to apply Gauss law? So first, we have to look at the symmetrical charge distribution, whether it exists or not. And I have emphasized this more uh, repeatedly. I have emphasized the symmetrical property of the charge distribution in a few examples, even before we reach this point. And the Gaussian surface, the hypothetical surface, the imaginary surface that we are going to choose to solve our problem, must be in the same. It must be such that the first surface is chosen such that d is normal to the tangential surface. So when d is normal to the surface, then the dot product of this dot product here. So this dot product here will become constant. when D is tangential to the surface that we chose, then is equals to 0. So therefore, we have to choose a surface such that the symmetry exhibited by the charge distribution. And finally, find the net charge enclosed by the Gaussian surface and solve for D and E. Okay. So we look at the point charge, the first application, a point charge. So as I have applied just now, so we will assume that this is a point charge at the origin. So imagine we are applying a hypothetical surface and enclosing the point charge at the origin. So the charge enclosed is equals to the flux to the closed surface. If we choose um, this Gaussian surface, and since that uh, the evaluation of the vector, I mean the flux, electric flux through the surface are all perpendicular. I mean the direction of the electric flux is in parallel to the surface, the normal surface of D. So what I'm trying to say is, so I'm just taking one of the, I'm just drawing the surface of the differential surface of the sphere. So remember that this surface here, the normal to this surface is in the direction of R, yeah? The normal to the surface is in the direction of R. So the surface is in the direction of R. So if the flux, the electric flux coming from the point charge Q, so from by Coulomb's law, we already know that the point charge, I mean the electric field coming out from the point charge is always in the direction of, is always radial, right? Is always in the radial direction. So therefore, by this Gauss law here, it means that the electric field is also the electric field direction coming from the point charge. It is also perpendicular to this surface, or in other words, it is parallel. It is parallel to the normal direction of the surface. It is, so if you try to pick this statement, I said the direction of the electric field coming from this point charge, it is perpendicular to this surface and or parallel to the normal direction to the surface, because this r cap here belongs, I mean the definition of the surface, the normal to the surface, is in the r direction. So the electric field, it is parallel with this direction, right? So if parallel, the dot product is vanish. The dot product uh, of Q, of this E here, of the electric field with this direction here, is going to be constant. So if it's a constant, then the constant term, of the electric flux can be factored outside the integration. And what is the interest is, so this arc length here is r squared sine theta d phi, and this arc length here is r d theta. Yeah. So the integration result as 4 pi r squared. So 4 pi r squared times the electric flux, but this is now a constant. Okay. So the index given here, just to indicate that the direction of the electric flux, it is in the radial direction. So eventually, and this is Q, right? This is Q. So eventually, D, the electric flux, is equals to Q divided by 4 pi r squared. So if therefore E, it is D divided by epsilon naught, and we have Q over 4 pi epsilon naught r square in the radial direction. And here we can see that Gauss law in some way, has also related in some way, proof Coulomb's law in some way, right? Okay. So come back again. I want to point out a bit on the symmetrical point of view, of how we choose the Gaussian surface. So typically, I mean, in typical example of how we choose the Gauss surface, there are only three types that we learn. Typical structure, typical geometric structure. Sphere, spherical, cylindrical, flat surface. These three, that's all, right? That is the charge distribution. So normally, when we choose the Gaussian surface, normally it follows the distribution geometry of the charge. So for a point charge, why is it a sphere? First, okay, imagine this is a sphere. So if you are walking along, if you are here, right? Let's say you are here, and you see, and you observe from this point observation. You look at here, okay? And now imagine that you are here now, and you observe this point again. It doesn't change, right? Because it's symmetry. So regardless how where you stand along the sphere, I mean on the sphere, on this spherical surface, re- regardless where you stand and where is your point of observation, the charge distribution remain the same, and therefore this imply symmetry. Okay, I will come again. So imagine yourself stand on the spherical surface. So from your observation point of view, regardless where you stand on this Gaussian surface, on this spherical surface, the charge distribution, it doesn't change. If it doesn't change, it doesn't, from your point of view, there's always consistent, the charge distribution, and therefore this will implies symmetry. Okay. So because regardless whether you stand here, or you stand here, or you stand here, it's always one. It's always at a point. So it doesn't matter. It will not change. It will not change. It's always at the point. Yeah, it doesn't change. So that implies we can apply Gauss law, and this is the appropriate, and therefore this is the appropriate Gaussian surface to be selected to evaluate the electric flux and subsequently the electric field. Okay, so let's look at another example. So we have infinite line charge. Okay. So now following what I have mentioned just now, the Gaussian surface now, will fall. We have to choose a Gaussian surface such that at any point we stand on the Gaussian we stand on the Gaussian surface and observe the charge distribution. Okay, the charge distribution must not change. The From our point of view, it will not change. So what I'm trying to say is, so assuming that if let's say the charge distribution is non-uniform, yeah. So assuming that half of this is rho v, some rho l prime, and the other half is rho l, yeah. Now, it is impossible to calculate the electric field at any point using Gauss law, because it's quite difficult to choose. It is quite difficult to choose a Gaussian surface where it's difficult to choose the Gaussian surface that is cater for this charge distribution. We can't. Okay. Okay, come again. So I will give you another point of view. So say that this is symmetry. The charge distribution is uniform. Is uniform. And now, what about a finite, not infinite line? What about finite? Okay. So say that this is a finite line charge. This is a finite line charge of length L. Yeah, of length. Let's say capital L. Let's say a finite line of capital L. Okay, capital L. A finite line charge of capital L. Gauss law fails as well. Even though, despite that the charge distribution, is uniform along the line, but Gauss law fails. And why, you will ask? Okay. Because imagine that you have a Gaussian surface, one closed Gaussian surface. So that the top part is open, yeah. For this cylindrical, this Gaussian surface cylinder, the top part is open, yeah, it's not closed. Same goes for the bottom. Okay, now come back to our discussion that if this is uniform and finite, not infinite, and finite with length capital L, why Gauss law? Why applying Gauss law fails? It is because imagine that you move your Gaussian surface up and down, yeah, up and down. So for a finite line, so this is length L, as I said, this is length capital L, and your Gaussian surface, let's say, move it to somewhere here. Somewhere here, okay, which is small letter L, okay. So again, now, as I said, imagine yourself standing on the surface and observing at any point. So of course, this is not symmetry anymore. So the symmetry properties is not obeyed, simply because if you observe at this point, or this point, or this point, it's all different, right? So it doesn't obey. It doesn't obey. It doesn't obey uh, the consistency of the the charge distribution. From from this point of view is different. From this point of view is different. From this point of view is different. Is the from this point of view is different. So simply because if we try to place the Gaussian surface along this line charge here. So if it's a finite of length capital L the symmetry is not obey. If we try to if we think that we can apply Gauss law to find the electric field at anywhere, so it is not possible. And what about infinite? So if you now you can see that if it's infinite, regardless where you move, regardless where you move, regardless how you move you rotate this Gaussian surface, or you move translational up or down the Gaussian surface, everywhere will be the same because it's infinite. So your point of view is always the charge distribution from your point of view is always the same because it is infinite, right? So let's say it extend to infinity, right? Extend to infinity. So the charge distribution is going to be symmetry, because regardless where if you stand here, stand here, stand here, stand here, it is always the same if it's extend to infinity. So if it's a finite, then you can't. So that's the reason why Gauss law has its own limit constraint for its application. So for infinite line, so Gauss law, we choose a cylindrical Gaussian surface. So this cylindrical Gaussian surface has a radius rho from the center of the axis, from this axis, and Q is the charge enclosed. Is the charge enclosed by this Gaussian surface. So it's equals to the flux through this Gaussian surface. So bear in mind, this Gaussian surface is an imaginary surface. It's a hypothetical surface. It's not there, but uh, virtually is there. It is not there, but virtually is there. Physically is not there, but virtually is there. So how we evaluate the charge? So if the line charge density is known, rho L is given to us, and therefore the Gaussian surface, the charge enclosed by the Gaussian surface, the total charge enclosed by the Gaussian surface, is simply just rho L times L, right? So we want to find what is the total charge enclosed by this Gaussian surface. So it's just rho L times L. And since that we knew, that from uh, the electric flux or electric field coming from an infinite line, the electric field direction is in the radial. It is in the radial direction. That means it is always perpendicular at any point. If let's say we want to evaluate an electric field contributed by this infinite line charge, so the direction of the electric field coming from the infinite line charge is always perpendicular to the point of interest. So therefore, it is radial. It is in the direction of radial with respect to the cylindrical coordinates. So okay. So the the surface, the differential surface, it is then for cylinder. So for cylinder, this is dz, and this is r theta, sorry, r d phi, sorry. So it's r d phi or rho d phi times dz. So the evaluation will be the integration variable of interest is d phi and dz. So d phi, the limit is from 0 to 2 pi, and dz is the length of the Gaussian surface, which is L. So therefore, we have L and L on the left-hand side and L on the right-hand side. So we can simplify this. So cancel off. It becomes 1. And therefore, the electric flux is equals to rho L divided by 2 pi rho. And it is exactly what we have when we use Coulomb's law to derive it. Okay. So if you encounter something in the questions, it says that uh, a long cylindrical charge distribution or infinite charge distribution, then straight away you can apply Gauss law. Straight away you can apply Gauss law to find the electric field at any point. Okay, at any point. However, if it's a finite, then unfortunately we have to resort to Coulomb's law. Uh, we have to resort to Coulomb's law approach to calculate the electric field. If it, and again, if it's a uh, non-uniform charge distribution, and then we have to resort to Poisson or Laplace. Okay, so this will comes later, but as I said, the course syllabus more focus on Coulomb's law and Gauss law. Our curriculum will be more focused on Coulomb's law and Gauss law. Okay. Um, so let's move on to the next example. So again, for infinite sheets of charge. So here again, we have applied Coulomb's law before. We have applied Coulomb's law before, and I have demonstrated to you for infinite sheet of charge. Uh, the evaluation of the electric field is always perpendicular to the sheet. Okay, to the infinite sheet is always perpendicular. So here we can see that what if we apply Gauss law? So again, our Gaussian surface is a cube. Okay, it's a rectangular cube, a closed surface. You can see it's a closed surface. And now, if this is finite, again, if you try to move around, this Gaussian surface, this rectangular cube, if you move around, if let's say you move to here towards the end, yeah. So assuming now it is a finite, so it's a finite charge. So I will draw this here just to demonstrate. If you are going to move this Gaussian surface towards the right, towards the edge here, or either towards this edge here, regardless whether we move here or move here, then you can see that at some point, okay, so the coverage of this surface, okay, again, if assuming yourself like if you let's say you stand on this surface, on this Gaussian surface, you can see that the charge distribution that covered by this Gaussian surface is not symmetrical anymore, right? So by applying, so that means again Gauss law cannot be applied for a finite sheet of charge. We cannot do that. So it is only applicable for infinite. So we want to maintain the symmetrical property. So if it's a finite, then Gauss law again fails to be applied, just simply because it is difficult to find a Gaussian surface that can maintain the charge distribution that is enclosed by the Gaussian surface. So therefore it fails. Therefore it fails for a finite sheet of charge. And as a result, Gauss law can only apply to evaluate the electric field or electric flux coming out from infinite sheet of charge. So finite sheet of charge is not possible, simply because that as I have uh, emphasized this again and again. You you have to imagine yourself always assessing. You have to imagine yourself looking at the charge distribution from I mean on the surface of this Gaussian surface, from this hypothetical surface. You stand on the surface, and if any point of view from any point of view, if it does not uh, obey uh, symmetrical charge distribution, so the Gaussian surface fail. So either there is no solution for this. I mean the Gaussian surface, there's no solution for the Gaussian surface to be chosen, or the charge distribution does not allow us to apply Gauss law. Okay, there is a fail scenario. So these are the typical scenario that where Gauss law can be applied. Typical scenario. So I'll come to, after this, I will ask you a quiz. Yeah, I will ask you a quiz. Uh, okay. Now, so applying Gauss law for infinite sheet of charge. Okay. So Q is equals to the flux coming out from this hypothetical Gaussian surface, and we knew that why is it only z component? Yeah, because for infinite sheets, the component, the electric field component, is only perpendicular to the surface. Is only perpendicular to the sheet. So there is no other component. So all the component, the electric field is pointing perpendicularly with respect to the charge distribution. This flat, the sheet of charge, infinite sheet of charge distribution. Yeah, so it is pointing perpendicularly. And why is it? How is it that the Gaussian surface is appropriate? Because if the criteria is that this is flat, and this rectangular cube is also flat. This part here is also flat. So what about uh, is there going to be, what about this kind of surface? I try to redraw this cube here. So I'm just drawing the top part. Yeah, I'm just trying to explain. Oops, sorry. So D is perpendicular, coming out from the infinite sheets. So it's perpendicular to this surface. So this is perpendicular, okay. And so this is, I mean, I'm just drawing one line. So what about here? What about, what about this surface here? I mean, sorry, what about this surface here? So this surface here, it is the 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 normal is perpendicular to the electric field, right? I mean, for this shaded area, the normal to this surface is perpendicular to the direction of the surface, right? So therefore, when we evaluate the flux on this surface is zero, because d dot this surface is going to be zero. So it is only the contribution is only this surface here and the top surface and the top surface. So this surface here and the top surface is only relevant. So the other surface is going to be zero, and therefore here it says top and bottom of the Gaussian surface. So for top and bottom, if the area represented by this Gaussian surface is ds, okay, and the total area of this Gaussian surface is A. This is A, and also this is also A below A. So we have the area A plus A. Okay, and on the left hand side, so that is the charge distribution. That is the surface charge distribution, rho s multiply ds. So this ds here is the Gaussian surface that we choose. So the total surface is A. The total surface is A. So top, middle, and bottom all is A. So therefore, Q is rho s times A. Q is rho s times A. So rho s is the surface charge density, multiply the area. So therefore, this gives us back the charge is equals to the flux, electric flux, times the area. So therefore, here is rho s times A equals to dz times 2A. So A and A can be eliminated, and therefore dz is equals to rho s divided by 2 in the z direction. And of course, in general, we will say that this is in the normal direction with respect to the charge surface, the charge distribution. So here again, we see that the application of Gauss law and what we have derived from Coulomb's law is the same. Yeah. So before we end, we will discuss. I will give you some quiz now. Okay. I want your input. I want your input. So we're going to talk about this next week. So there are two things I want to discuss. First is the quiz. So let's say you have 2-point charge. I have 2-point charge in space. I have 2-point charge in space, Q and Q. I have 2-point charge in space. Is there any appropriate Gaussian surface that I can apply to evaluate the electric field everywhere in space? So this is the first This is the first quiz. Okay. If I have a sphere, okay, like this. If I have a sphere like this, imagine it's a three-dimensional sphere, solid sphere. So the charge distribution is over a volume, and also the same go on the outside. So the charge distribution is also it is also over a volume. So this is the second question to you. So I want you to type in your answer. The third one. Okay, let's say we go for the second one, one and two first. The third one will come later. So is it possible for scenario one, I apply a Gaussian surface which is spherical? Can I apply a spherical Gaussian surface to evaluate the electric field everywhere in space with these two point charge here? That means, imagine I'm going to apply a spherical Gaussian surface like this, a sphere, enclosing the two charge. Can we evaluate the electric field everywhere? Is it possible? Yes, for question one, and also for question two. If I'm going to apply a Gaussian surface, again, a spherical Gaussian surface, is it possible for me to evaluate the electric field? So one and two. So type your answer in the chat box. Yes, one, yes or no. Two, yes or no. Okay. I want you to uh, try to. I want to see your understanding on how you look at the charge distribution. No, yes. One yes, one yes, one no. One no, maybe yes, two yes, one no. Okay, one no. No and yes. Yes and yes. Okay. The supposed answer is no and yes. So the supposed answer is no and yes. It is not possible to evaluate the electric field using this Gaussian surface. So it is quite impossible to, because imagine now, so imagine now, if this is a sphere, remember this is a solid, hypothetical sphere. So if you stand here, looking from here, so the charge distribution compare that you are standing here. So if you stand here and stand here, so if you look from here, the charge distribution is going to be a dot, right? A dot. If you look directly, from this axis, it's going to be a dot, right? So if you stand at this point, here, so it's going to be, if you, let's say this is, so you stand at this point, so is, if you look down, it's going to be a dot, right? Coming, but it's going to be a single dot, single point. So since it's a point charge, but if you stand at this this position, is going to be 2-point charge. And again, if you move slightly above here, the symmetry is not, it is not maintained. So so you stand here, stand here, stand here. So regardless where you stand, the charge distribution is not maintained. So that means from your point of view, the charge distribution is not maintained. If we're going to choose a spherical uh, uh, Gaussian surface. If you choose a spherical Gaussian surface. Okay, what about 2? So this is no. Yeah, this is no. What about 2? So 2 is yes, because if you stand here, you look through here, even though the volume charge density, the green and blue is different, but if we stand here, so if we look through here, this remains. I mean, the charge distribution at this point is remain, and also this is remain. So regardless where you stand now, so if you try to stand here, so again, this portion here doesn't change, this portion here doesn't change, and same goes for here. So again, if you see from this perspective, the charge distribution maintained. So because this is a sphere, outside is a sphere, and if we choose a Gaussian surface is a sphere, so everywhere we look at, it maintains, the charge distribution maintains. So one last question to you, one last question before we end. What about this? Now I give you a sphere. One have a different charge distribution highlighted in red, and another one has a charge distribution highlighted in black. Can we use a Gaussian surface, which is a sphere, a spherical Gaussian surface? One last question for the third scenario. So spherical Gaussian surface. So is it possible? Three, no, no. Yes and no. Third, they cannot be yes and no. It's no, Kaibun. So Renji also no. Yes. The answer is no for third scenario. We cannot use a spherical Gaussian surface to evaluate the electric field in this case, because if half of the hemisphere with different charge distribution. So again, I have say that if you stand here and if you stand here, the charge distribution is going to be different, because if you stand here, the charge distribution is on the red on this red hemisphere, and if you stand here, the charge distribution is on the black hemisphere. I mean, the charge distribution is different. Therefore, spherical Gaussian surface it cannot maintain the symmetry property if we use this spherical Gaussian surface. So we can't. So this type of scenario, if the charge distribution is not symmetry in this case, so the Gauss law, or we cannot find any appropriate Gaussian surface that can be applied using Gauss law and to calculate the electric field. yes, we can calculate the flux. So how we calculate the flux? So the flux is just 2q. If we can apply any surface to calculate the flux. Flux is just the total charge, right? So yes, I can apply any Gaussian surface, and I say, okay, the flux coming out from this Gaussian surface is 2q. You can do that. You can say that. But we cannot find what is the electric field and electric flux density. That's the problem. Because when we try to evaluate the electric field and electric flux density, we always need to find that we always need to find that the direction of the electric field or electric flux density perpendicular to the surface, perpendicular to the Gaussian surface. Yeah. All right. We will end here, but before we end, just a quick one. Next week we are going to have a test. Okay. Next week we are going to have a test. Um. So the test covers Gauss law until Gauss law only. Gosh, is only Coulomb's law and Gauss law. Okay, and it's only two questions. Okay, it's only two questions. So most probably it will be Thursday. We're going to had it in Thursday, but I do not want to use Thursday as the. I mean, just to waste Thursday for the test. But what I want to suggest is I want to have a lecture, an additional lecture on top of Thursday. So the previous one we had it on Monday, right? I remember something like that. Monday or Thursday, I can't remember which one is which. What is the last lecture replacement that we have? Friday, is it? Monday or Friday? Monday is lecture or tutorial? I can't remember. So let me check. Just have a quick check through my intranet. So week four we have a replacement tutorial, replacement lecture. We have it, right? When? Oh, we have it on Friday, replacement lecture, 2 to 4. Okay, so I suggest 2 to 4. No, maybe 2 to 4 I use it as the additional lecture. And Thursday is going to be your test. Is it okay? So Friday 2 to 4 will be your additional lecture for next week, and Thursday is your test. So the test will be 1 hour 15 minutes, or yeah, roughly that. Basically, it's 1 hour, 15 minutes for you to upload the solution. Basically, the test will be 1 hour and 15 minutes for you to upload the solution. And that's going to be your midterm test. And after the test, we're going to discuss the solution directly. Okay, so everyone, I think everyone's okay with the arrangement, right? All right. So that's all for today. Thank you, everyone.